Okay, so today we're going to learn another kind of NAND gate. So we're going to build this NAND gate from the 4093 IC. Alright, this is the pin number 5 plus for the voltage, for the power. The power is the IC. So 5, 14, and ground at pin number 7. Now, we have learned actually last time the NAND gate. What's the difference? All right, this is 4011. Now the limitation for this NAND gate is that if you use a switch, for example, to turn on this input 5 volts to the A and B, right? A and B, and the switch, the problem is that you're going to create noise, because when you turn on mechanically, you're going to have some pulse, right? This generates the noise to the output. Okay, so to overcome that problem, we use the 4093, and it's the same. This is NAND gate, NAND gate, and the way that we construct this is the circuit diagram we're going to build later, and this circuit is going to reduce this noise for the output. Now we will see later. Now, of course, we have to revisit 401 and see what happening if we have to switch the mechanical switch for the input. This is the circuit that we built last time. This is 4011, and we use the this pin 1, 2, 3, 1, 2, input A, input B, and then they are connected, and then have this power. Then we have the switch, push on switch to 5 volts. So this is 5 volts to our power supply here. So we can turn on power supply. We already checked it's 5 volts. Alright, then we output to the oscilloscope. Okay, so this is the output from pin number 3 to the oscilloscope channel 1. As you can see, this is now there's a little bit noise built out. So it's in the ground level. Alright, it's supposed not to be ground, so we have to short that. Alright, now the input, as you see, input should be 0. So 0 to input A, 0 or low level, low voltage, 0 voltage to input B. So you have this, so you see this is exactly 5 volts as the output. So you see that. So this is output is 5 volts, right? You can check. Now if I turn it on, you see how noisy is that going to be, right? Alright, so this, you see this response. You can see the quick response from the oscilloscope. Alright, now it's turned on. The switch on means you have input A and have input B as 5 volts. So you have high signal for both input A and B, and the NAND gates should have the output as 0. This is what you see. Right, and you see the noise generate in this gate. So this is the problem with the 4011 and to use with the mechanical switch. So to overcome that problem, or to reduce noise in the circuits, we will have this circuit built by using the 4093. So similarly to 4011, we have these 4 NAND gates. So this is 1, 2, 3, 4. All right, so we just use this, the 1/4 of this IC, and this is how we build. So, all right, we have to change this one. Just put a switch, and then put that switch in parallel with the capacitor. We have this capacitor. So this is 1 microfarad capacitor connected with the 10 kilo ohms resistor. So this is this 10 kilo ohms resistor connected to the 5 volts power supply. So we have fit in the 5 volts, all right, 5 volts, and then to 1 microfarad capacitor, and then ground. And in parallel with this capacitor, we have this switch. Okay. Now we have this circuit ready, and we use this channel 1 as a B. This pin 1 as B input A, and input B. They are connected, and then have this input feed through this the junction of between the resistor and the capacitor. Then we have the switch. Okay, so we have this power drop, voltage drop across this resistor, and the voltage drop across the capacitor. If the switch is off, then we have this voltage drop. It's like a voltage divider. Now, if the capacitor here, if no short circuit for the switch, then you will have the high voltage drop across the capacitor. So the input for the circuit here is 5 volts. So you have the high input, high signal of 5 volts, or 1 input for A and B. So you have input A, input B, and the outcomes to be 0. So because it's NAND gate, 1 and 1, you will get 0 output. So, all right, we have to see. So far, we have to check. We have turned this. We use this output from 1493. Right, forget about this 4011. Okay, so this is the circuit. All right, now as you see, we have these. We have the high input A and B, and the outputs we expected to have is 0. All right. Oh, sorry. Let me see. You have the 1. All right. Back to 1493 circuit for lab 17. Okay, we constructed this circuit. Okay, so previously I forgot to power this IC. So we have this 5 volts to pin 14, and then ground at pin 7. So because of that, we cannot get the result that we want. So again, this time we have the input A, input B, right? They are connected. So they have the same input from the power supply, 5 volts that I use. So 5 volts, this current feed to the 10 kilo ohms resistor, and then there has a junction, and then the input 5 volts signal we will go to A and B. So this is the 1 microfarad capacitor, and then go to ground. Parallel with this capacitor, we have this mechanical switch, all right, push button switch. So let me explain the circuit. Okay, so we have this input, right? This resistor and the capacitor, you know, is act like a voltage divider. So this current is flow through 10 kilo ohm resistor, and then flow through the capacitor, and then go back to the ground, go back to the power, the ground of the power, go back home. In this case, I always telling you that to make a loop, then these two components, they act like a voltage divider for the input to A and B. Okay, so if the switch is not turned on, that means open circuit, and what you have is that you have this voltage drop between this, you know, this junction and the ground. You're going to have 5 volts because this component is going to be a high resistance, all right, capacitor. It's like an open circuit for the DC circuit. So this is going to generate 5 volts signal to A and B. So you have high input to A and high input to B, so 1 and 1. And then the output you expect that to be 0 because it's a NAND gate. So this is what you have. I have this oscilloscope to let us see the output of the NAND gate. All right. See clearly, it's flat, it's clean. This is a clean signal. All right. Now what I have to do is that I turn on the switch, and you notice what happened to the output signal on the oscilloscope screen. Right. Look at that. How clean it's going to be. You can see when I turn it on. All right. You're going to have about 5 volts, the output signal, and then you release the mechanical switch. It's off, and the output is very clean signal of 0 voltage, 0 volts. On, off, on, off, on, off. Okay. So this is necessary for the digital circuit. So we built this, all right, circuit by having this input signal to the A and B, and this is going to be a clean signal if we have this resistor and capacitor. So what happened to this capacitor is that if you look at this circuit diagram, I can explain to you. So you have 5 volts. This is from your power supply, and the current flow, and then charge up. It's going to charge up this capacitor, all right? And then you're going to have this slope back to the power supply, ground, means going home. And when this is done, this build up charge, and then if this charge is built up, it have to be stopped at a moment where the VC, or the voltage drop across the capacitor, is equivalent to 5 volts. And that's why you have this 5 volt input to the A. I call this input A, input B. And then if you have 0, or if you have 5 volts, or high signal, high input to A, high input to B, 1, 1, and then you expect to have the output signal as 0, all right, because this is NAND gate, not N. That's what it means. Okay, so you expect to have 0. This is what we have. Okay, now the signal is clean now because you have this clean 5 volt signal. Now when the switch is on, for example, now you have this connect, that means this is going to discharge the capacitor, all right? When this capacitor is discharged, that means the voltage drop across the capacitor is to be 0. All right, there will be no charge accumulated in the capacitor. You expect to have 0 input signal. So you have 0 volts, 0 volt to A and 0 volt to B. Then if you have 0, 0, and what you expect as the output, you're going to expect to have 1 or high or 5 volts in this case for your output signal. That's what you have. Okay, this explains the circuit for using the 4093. Okay, the next part B, divided by 2 flip-flop. So we are using this 4013 IC as a flip-flop circuit. So flip-flop is the basic counting unit for electronic circuitry. And the IC we use, 401T, has actually two flip-flops in this case, or FF. So we have this another one here, and they are connected to this 6 leads. So we use half, that's why they say half of the 4013 IC. So we use this side, and this Q1 is output, Q output, and this is Q bar. And clock, usually you have the signal in, and then the reset, they use R, data, and set, and we have this ground. So to power this IC, we have these 5 volts into pin number 14, ground, pin number 7. All right, so this is what you have in your lab instruction. So Q as the output, and then we have this input. We input this power signal. So this is going to be the high. This is going to be low level, high level, low level. So this is going to be 1 signal, 0, 1, 0, 1, 0. And we're going to fit into the clock. And then we want to test what is come out. Okay, so at the Q. So according to this picture, we're going to construct this circuit. This is what I have built. So the power from the DC power, I set 5 volts normally for this IC. So 5 volts is very common voltage for the IC. And of course we have the ground. So this is connected to 14, ground at pin number 7. Make sure I have the right, yes, 7. All right, pin number 1 is Q1, Q bar, clock, 1, 2, 3. So Q is the output that we want. So output I connected to the oscilloscope. All right, and the 2 is Q bar is connected to data, which is pin number 5. Let's make sure I got it right. And then you have this clock at pin number 3, yellow wire. So I have to fit in this power signal, square wave signal from the generator. That's what we have, generator. I set this 1 kilohertz, not too high, not too low, and the peak to peak is 5 volts, which is reasonable. And the reset, which is pin number 4, is connected to set, which is pin number 6. It's right. Okay, offset, and then we try to fit in this square wave signal to number 3. All right, so I turn it on. So this square wave. So it's ground, and then the output from the Q, this is pin number 1, and we have also ground. So this is the second channel of the oscilloscope. Now this is what I have. This is the result. Okay. This is a flip-flop, like explained in your manual, right? The first pulse, if you consider this is first pulse here. All right, the first pulse, and this flip-flop is going to output as high. And when you have the second pulse, this is second one, then the output from the flip-flop is going to be lower. So you have this, actually this is 1, the first pulse, second pulse, and then the flip-flop is going to flip to 1, and then second pulse is going to flip to 0. So this is called the flip-flop. So the first pulse changes the output to high, and the next pulse changes the output to low. Is what it means. Okay, this is the result that you have. You can put in your report and then explain and describe what the circuits means by divide by 2. There's meaning. This meaning of the flip-flop as a divide by 2. Okay. Hopefully you get this idea. It's basically done for the part B. No, I may not explain the channel 1. Channel 1 is from the generator. This is channel 1. This channel 1, which is yellow signal. This is input to the clock, and this is output. This blue line, the channel 2, is output signal from the flip-flop. All right, so hopefully this is clear for you guys. Okay, this is part C, analog switch control of lab 17. So we're going to learn CMOS 4066. So this IC is called core bilateral switch. So actually this IC functions like a switch, and it can be controlled. The switch can be controlled by the digital signal. Right. And each chip or IC contains 4 switches. This is the schematic diagram of the IC 4066. So we have the powers, like usual. We have to power the chip, the IC at pin number 14. I use 5 volts, but you can power this IC from 5 to 15 is be all right. And pin number 7 is for ground. So we have this. You can count. You have the four switches. So input, output, 1, 2, and this switch is controlled by the pin number 13. So this is called control A. And then we have another switch between 3 and 4, pin 4, 3, 4. So it's controlled by pin number 5. So they call it control B. Similarly for control C. So control C is the switch 8 and 9, and then 10, 11, so on. Okay, so part C asks you to like simple check whether it's working. So you can have, for example, I'm going to use this the first switch, which is pin 1, 2, and controlled by 13. So I'm going to have this, like say for probably you can have this signal 5 volts input, and then this will go to, let's say, your output, let's say oscilloscope. This is out to oscilloscope, for example. Okay, very simple. And then the pin number 13, I will have the input from, let's say I follow the instruction. You can have the generator, and I'm fit in maybe a square wave with peak to peak VPP 5 volts. Okay, and this is the circuit I have built. And okay, so alright, power 5 volts from the power supply to pin number 14. This is pin 13. Pin 7 is ground. You have to go home to the power supply. And this is pin 1 input. I connected to 5 volts from the DC supply, power supply. This is fit in 5 volts for input, and then output I connected to the channel 2 of the oscilloscope. Now I have not turned on the power. You see all the signals are showing 0 volts. Okay. So if I turn on the power up is 4066. Okay, so this is a signal fit in, square wave fit in. If you have this high, you're going to turn on the switch. If you're low, you're going to turn off. So what you have, let's see, I've not turned on this. So I have 1 kilohertz, 5 volts, peak to peak. Okay, so if you turn on, all right, this is what you have. So channel 1 is my signal, input signal from the generator, which is a square wave, 5 volts, 5 volts peak to peak. Now the blue line, the channel 2 is the output from the switch number 1. Okay, so this switch, all right, this is the result. Now if you can see that this is to control A. It's not so clear. All right, you have this high level. That means you have this digital signal in this signal, high voltage signal to the controller, and then it's going to turn on the switch. That's why you have this about 5 volts. This is 1 division, 5 volts. Turn it on, so you have switch on, and then you see there's a decaying. I do not know why. All right, this is probably that the control is off. You don't have this signal, lower signal or zero signal, or low signal or low voltage. You're going to turn off the switch. All right, it's not suddenly turned off, but it's slowly turned off. Okay, similar for the next signal. It's on. The controller turn on the switch, off, on, off, so on. So this is the result for part C, the first part of the part C. Now the part C is also asked connect input 5 volts non-stop. Yeah, this is what we observe. And try using an input of greater than 5 volts. So I can tell this, we input the 5 volts, right, for the pin 1, we fit in 5 volts DC signal from the power supply. So now I'm going to increase So this is the knob. So I increase. So now I have 5 volts. So I increase more than 5. See what happens. So I increase more than 5 slowly. And then this is what you observe. Alright. So I increase now is up to 12 volts. So I reduce back to 5. And below 5, close to 0. This is 0 volts output. 0 inputs, and then you see its output 0. I increase the input to pin 1 slowly. Now back to 5, above 5. Okay, now it's 10 volts. I hope this is clear for you guys to see. Alright. So this is a change. If I change the input, which means here, if I change the 5 more than 5, you know, I will have this. I will not have any off, so it doesn't work properly if the input is more than 5 volts in this case. So hopefully this will help you to get the answer for the first part of part C. For the second part of part C, so what they ask, they want you to like connect the output of 4013 that we had, alright, to the control of the 4066, alright, and keep the function generator connected. This is the schematic diagrams of 4013 and 4066, how we connect this together. So you say that the control of the output of 4013, the output of 4013 Q for the pin 1, you have to connect the wire to the control of 4066. So this is going to control the switch, turn on and off for the switch for the power supply 5 volts fit into pin 1 of 4066 and then output to pin 2 to oscilloscope of channel 2. Of course, we connect channel 1 of oscilloscope to the generator that we have. Okay, now the generator signals is fit into pin number 3 of 4013. So it's a square wave signal, and then the rest is the pin 2 connected pin 5, pin 4 connected pin 6, then connect to ground. So these two ICs are power. Alright, we have this power connected to 5 volts, so we can like make a connection parallelly. So, and then the ground for pin 7 of 4066. So this is pin 7. So we power both chips with 5 volts. And this is the circuit diagram, or the schematic diagram of second part of part C. So this is the circuit I have built based on the circuit diagram we have. So I have turned on everything, and the 5 volts peak to peak, 1 kilohertz. Remember, we use load high Z, and the output from the 4066 pin number 2. to the second channel, which is blue. And this is the result we have. And of course, combined with the two ICs, so this is the input signal to pin number 3 of 4013, and then this is output signal. And we learned from 4013 is a flip-flop circuit, so it means the first pulse or the first high signal is going to turn on, all right, and then the second one is going to turn off. So that's why you have this signal we call the divide by 2. All right. Now, of course, I can repeat the same procedure by increase this power, increase the V in for 4066 from 5 volts to, let's say, 10 volts. And you see what's the result we have. All right, so I'm going to go very slowly. So I'm increased from 5. All right, now you see some kind of noise, and then you're going to have this more than 5, probably it's about 6, I can say 6 watts. Right, it's not working properly now. It's just turned on the switch. And the switch is all on up to 10 watts. All right, this is the result for the second part, or part C. All right.